Welcome to Module 4, Lecture 4 of Concrete Technology. And today we shall be discussing ACI 211 method, mixed design of concrete, right. So, we have earlier discussed the Indian code 10262 method, and then having discussed the Department of Environment British practice, which is quite close to the Indian method. Now we can look into ACI 211 method. So generally we will discuss this and some example we will take. Now of course, although I am writing this as step 1, if you look at the ACI 211 report, the step 1 is stated to be the determination of slump, and step 2 is given as determination of maximum size of aggregate. Now these two are similar to the earlier method, and if we are doing it by Indian method or in India using the ACI method, then we shall be actually using the IS method or IS 456-2000 guideline for specifying the slump or fixing the slump and fixing the nominal maximum size of aggregate. Having done that, next is the step 1 part of it, which will be actually step 3 in the ACI method or ACI report 211, but here I am calling them as step 1. So that is actually estimation of mixing water, and that we do from a table, right, which is given below. That we do from a table which is given below. This table has got two parts. First part is related to the mixing water, and second part gives you the amount of air entrainment, right. So you determine the air content, amount of air content. So determine amount of air content and mixing water together from two tables. One is for non-air entrained concrete, another is for air entrained concrete. For example, this table, if you look at it, the amount of water depends on slump. This is of course we have taken in centimeter, 1 inch, 2 inch, so corresponding to this. In fact, ACI 211 gives you now SI, everything in SI unit as well, together with the US customer unit. So slump we have written in centimeter, and maximum size of aggregate corresponding to this amount of water for non-air entrained concrete is given. And you can recollect in both the other methods we discussed earlier, the amount of water has been a function of the MSA, the required workability in terms of slump and BB, etc., and also of course the shape of the aggregate. So here it is given in terms of the MSA, and non-air entrained concrete and air entrained concrete will have some amount of difference in water requirement. That is because air entrainment, although its main purpose is related to freeze thaw resistance, improves the workability somehow, makes it plastic, makes the concrete a little bit more plastic, therefore more flowable, therefore water required will be somewhat different. So, non-air entrained concrete, these are the values given for slump from 2.5 to 5 centimeter, that is 25 mm to 50 mm, and as your aggregate size increases, you can see that water content reduces, and as your slump increases, water content increases again. So, it is the principle is same, idea is same, after all it is the same kind of concrete only, and water content is what you can find out in the beginning. For air entrained concrete, these values water content are somewhat less, because as I said, air entrainment tend to improve the workability. Therefore, if you see this is 181 for air entrained concrete, for non air entrained concrete the same value is, for non air entrained concrete same value was 207. So, the what air water content for air entrained concrete is much less, and as you increase your slump, water content increases. This was 243 for non air entrained concrete, for air entrained concrete this is 216, and as you go along this direction it reduces. So, this is the first step. If you know the slump and MSA, then this will be the first step. So, you determine your water content for the given MSA and given slump. Then air content, corresponding air contents are given. For non air entrained concrete, typically you can take the air content in percentage as 3% of the total volume, 2%, 1.5% and 1% for MSA, increasing from 9.5 mm size to 37.5 mm size. That means higher bigger the MSA, more the MSA, packing is better. So, your air content reduces down, paste would be reducing. So, air content actually reduces down, and that is what is given for non air entrained concrete. For air entrained concrete, however, this will be much higher, and that would depend upon the dosage of the air entrainment. Now, this is suggested that minimum air content, recommended air content for different exposure condition. For extreme exposure condition, this air entrainment should be 7.5 to 5.5 depending upon MSA, and for mild exposure it is 4.5 to 2.5. So, your dosage of air entraining agent should be such that it gives you much higher, at least this recommended air content when it is exposed to extreme freeze thaw condition, mild condition as defined by the code, all right. So, mild, moderate and extreme situation as defined by the code, all right. So, this is the air content, right. Now, so far therefore, we have determined the water content. Air content does not have direct implications at the moment, but water content has got direct implication at the moment in order to calculate out the other component or other component in the mix, proportion of other component in the mix, all right, proportion of other component in the mix. So, having determined the water content, the next step would be to determine the water to cement or water to cementitious material. Now, American method of course uses 28-day cylinder compressive strength rather than the cube strength. It uses 28-day cylinder compressive strength, and therefore, the recommended water is given for average cylindrical compressive strength at 28 days in terms of MPa, corresponding water to cement ratio by mass is given in terms of for non air entrained concrete. So, this is given in a table. So, you can distinguish actually from the other two method First of all, in Indian method, it is suggested you take it from experience or the durability requirement. In the British DOE method, strength versus water cement ratio curves are given. So, you have to pick up one of the curves. Here the recommended water cement ratio is given in terms of a table. So, from the table you pick up for air entrained concrete and non air entrained concrete. So, depending upon the strength, in fact, here is only a part of the table, the complete table will have more data. So, cylinder strength is average cylinder strength is given. This is actually average strength, average 28-day cylinder compressive strength, right, average, which is something similar to our target mean strength, except for the fact that it is actually cylinder strength, right. And perhaps we have not discussed this so far, but when we discuss about strength or factors affecting strength of concrete, we will be seeing that the specimen shape, especially in terms of L by D ratio, has got an effect on the strength. So, cylinder strength, this is about 0.8 times F cube strength, FCU. So, FCY, if I call it, cylinder strength is equals to 0.8 FCU. In other words, the cube strength is higher than the cylinder strength. So, when you are using this, let us say like in India, where we generally use cubes, there if it is an M25 grade of concrete, then cylinder strength will be 25 multiplied by 0.8, which will be actually 20. Or if it is if it is 25 here, correspondingly 25 divided by 0.8 will be 31.25 or whatever it is. So, somewhere 25 will correspond to M30 grade of concrete, close to that. So, this is while adapting the adaptation, for adopting this in Indian scenario, Indian condition, you have to convert them to or convert cube strength to the cylinder strength. So, correspondingly you can choose the water cement ratio given there, for non air entrained concrete and for air entrained concrete. Largely, of course, in India we do not use air entrained concrete except for Himalayan region, where air entrainment become must, because there is a problem of freeze thaw action in deterioration due to freeze thaw action is possible in the Himalayan cold region. Otherwise, generally non air entrained concrete is what we should be using. So, here the water cement ratio is straightforward, obtained from the table. We obtain it from the table, straightforward you obtain from the table, water cement ratio is obtained from the table. But what is average strength? You see, when we are talking of IS method, we talked of target mean strength FM, which was FCK, that is your grade strength, characteristic grade strength, plus 1.65 sigma. We are always talking about 28-day strength only, and age is not varying. So, we were talking of target mean strength. Now, here the average strength represent something similar, average strength represents something similar. So, these are essentially the average strength, and corresponding water cement ratio you can determine. Now, how do you determine this average strength? Well, this is slightly different than the other code. First of all, it says that you from 30 consecutive results you can determine the standard deviations, right. From 30 consecutive results you can determine the standard deviation, and if it is not available, then you take the average strength FCR as FC plus 6.9, FC plus 6.9 when the cylinder strength, grade cylinder strength is, characteristic cylinder strength is less than 20.7. If it is more than 20.7 and less than 34.5, then you add 8.3, and if it is greater than 34.5, then you add, oh, this is wrong, this is not, you add 1.1, this is given as 1.1 FC plus 10.5. So, the value is different, this is not correct, value is different, I think we have the formula separately. So, this is not sorry, FC plus 10.9, not 1.1, FC plus 10.9. So, anyway, this is FC greater than 34.5, you have the average strength more than 6 point, more than added by some number. So, basically it specifies what should be the strength, depending upon what is the cylinder strength, right. So, average strength, if you do not know the standard deviation, but when you know the standard deviation, the average, when you know the standard deviation from 30 consecutive data, or you know it from 2 sets of 15 consecutive data, so that you can find it out as under root of S1 square plus S2 square. S square can be written as S1 square plus S2 square, right. So, S2 15 set of data if you have available. So, that S is known to you. So, when you know S, you find out the strength as maximum of the two given below, that means this, either of this or this. So, when nothing is known, you find out from the table, when nothing is known, you find out from the table, when it is known, then you find out from this two formulas equation, whichever is greater, maximum of the two given below, that is this is your cylinder strength plus 1.34 standard deviation, okay, and or this plus 2.233 S minus 3.5. Actually, minimum acceptable strength is Fc dash minus 3.5. So, minimum plus 2.33 Fs is a average strength. So, average strength is minimum strength plus 2.33 S, that is, it is again from that normal distribution curve. So, 2.33 S to cover specific percentile. So, is the case we had 1.65 to cover 95 percentile, right. That means only 5% would be 5% would be showing strength less than this. Here this value is somewhat different, because it is not 5%, and this minimum strength is stated to be this. So, minimum strength plus 2.33 S should be the average strength. This is again with certain confidence limit. So, whichever gives you higher, based on this, whichever gives you higher, you choose the one whichever gives you higher. So, that you choose, or you choose from the table that is given simply in terms of Fc dash plus some value. So, that is how you choose your average strength, and then go to the table and find out the water cement ratio. So, you have found out the water cement ratio. So, you can find out the water cement ratio, and we have also found out the water content. So, for this, it is all, again I repeat, it is for the cylinder strength. So, average cylinder strength is known, and therefore, correspondingly I found out the water cement ratio. And when I found out the water cement ratio, also the water content, I should be able to find out the cement content. So, cement content I should be find out. But before that, just to mention that S can also be obtained from two data sets having 15 data each, as S1 square plus S2 square is equals to S square. So, that is how it can be found out, right. That is how we can find out. So, the next would be calculate cement content from the water content and water cement ratio required for durability or strength. Well, durability again controls water cement ratio is controlled. You have a maximum limit of water cement ratio. You have a maximum limit of water cement ratio. So, therefore, durability is again controlled. Durability controls the water cement ratio. So, you have maximum water cement ratio, and from the strength consideration you have found out the water cement ratio. So, whichever is lower, you choose that water cement ratio, and based on that you find out the cement content, because you know W by C, you know W, you can find out C. C can be obtained. C can be obtained. So, you see this has got some sort of similarity up to this stage with the methods that we have looked into earlier as well. That is, DOE method also does the same thing. First finds out the strength, water cement ratio from strength, and water content from workability, MSA, and whether it is a crust or natural aggregate, from that kind of, other words, shape of the aggregate. So, you find out the water content, and once water cement ratio and water content is known, C can be obtained. Now, here it differs. Here ACI method differs, as we can see it differs. ACI method would differ from earlier methods. DOE methods used wet density concept, while IS method used, we use total volume, sum total of volume must be equals to 1 meter cube. So, conservation of volume principle. Wet density is also similar, but here what is done is you find out the dry eroded density of the aggregate, dry eroded density of the aggregate. That means, what you do, you pack the aggregates, coarse aggregate in 3 layers, aggregates in 3 layers, and find out, because volume of this is known, how much is the mass. This volume we can find out first by filling in with water, volume of the container, then put the aggregate, and find out how much is the mass of the aggregate. So, if you know this mass, then this will be dry eroded density, dry eroded density. So, you know the dry eroded density, and dry eroded density, right. Dry eroded density of this is known, that is mass in unit volume is known, and if I know the volume occupied by the aggregates, right, in the overall volume, then this, if I multiply by this dry eroded density, that will give me the amount of coarse aggregate present in the overall concrete system. So, estimate the coarse aggregate content for maximum size of aggregate and fineness modulus of sand from the table. This, the coarse aggregate content in volumetric coarse aggregate content, or proportion of the coarse aggregate content in fractions, that we can find out. We will just find it out just now, right. From the next table, we will look into the table, but before that I just make, I would like you to recollect, when we discussed about aggregate, remember we talked about fineness modulus. The fineness modulus is average, it is the average sieve size in some form, that is what we have seen. So, fineness modulus defines the fineness of the sand, right. If you can recollect, fineness of the sand is defined by fineness modulus. So, in the next table we will come back to this one again if required. Fineness, if you see volume of coarse aggregate per unit volume of concrete on dry eroded basis is given as by this. So, you have, as your maximum size of aggregate increases, here we have taken also for 50, 37.5 and 50, and there are large numbers are all available. This is the fineness modulus of the aggregate, increasing along this direction, and this is my MSA increasing. So, total aggregate content increases, in other words, your sand content to decrease as I have more sizes, as the MSA increases, total aggregate content increases, because sand content would reduce, their sand content would reduce because it will have a better packing. So, sand content would reduce, and this is related to the fineness modulus of the sand, right, fineness modulus of the sand. As the fineness modulus increases, the volume proportion of the sand again would reduce, because this has something to do with the overall grading or overall packing of the system, right, overall packing of the system, overall packing of the system, all right. So, overall packing of the system, because higher the fineness modulus, it means you go to coarser, you go to the coarser size, overall size will be coarser, which means you have got a better grading of the sand itself, better grading of the sand itself, sand themselves pack better, and they have different sizes, more larger sizes also available in them. So, they occupy more volume, they pack better, and therefore, you know, they pack, they do pack back, overall packing is better. So, sand volume reduces along or aggregate, coarse aggregate volume reduces as I go along this direction. In fact, sand volume increases, volume overall proportion of the sand actually overall proportion of the sand increases, overall proportion of the sand or sand volume increases, because coarse aggregate proportion is reducing, because sand itself has got a better packing, and more the larger sizes are also there. So, it fits into overall grading better. The space here will be filled in by less sand. So, that is why you find that fineness modulus, with higher the fineness modulus of sand, this is decreasing, and as we increase the MSA, this volume, aggregate volume increases. So, the proportion of the aggregate volume is given by this one, this particular table. So, supposing you find out that this is 0.64, and you know the dry eroded density of the coarse aggregate, multiplied by this to get the mass of the coarse aggregate that is present. It means that in your total aggregate, 64% will be the aggregate volume, 64 will be the aggregate volume, and rest of the volume would be, volume of the coarse aggregate will be this much, rest of the volume would be the paste and the mortar altogether. So, 64% will be volume would be occupied by the or 65% by the mass would be occupied by. So, dry eroded density gives you the mass per unit volume, and only 64% of that would be occupying the total space in concrete, rest all will be filled in. So, in 1 meter cube, you know, dry eroded density gives you how much solid aggregate would have gone. If you multiplied by this fraction, that much will be the aggregate content in the coarse aggregate content in the concrete. So, obtain coarse aggregate content from dry eroded density and above information, that percentage that you have got, and then determine the fine aggregate content by subtracting the sum of the volumes of coarse aggregate, cement, water and air content from the unit volume of concrete. So, then again use the conservation of volume concept, and you can determine the total, determine the fine aggregate content, and that is how you have got the proportion. So, you have got the proportion. So, we can look into now example, similar example as we have done earlier. Well, Indian M20, not M25 will not be the correct statement. I will say 25 is the cylinder strength. So, this is not 25 MPa cylinder strength. Cement, of course, we are using OPC for the simple case of an example. If it is M25, this would have been 20 MPa cylinder strength, 20 MPa cylinder strength, but we are not using that. In fact, ours is higher strength. So, 25 MPa cylinder strength, corresponding concrete strength would be, cube strength would be 25 divided by 0.8 would make it 1 point, right, 25, 31. So, 31.25. So, somewhere around M30 grade of concrete if the cylinder strength is 25 MPa. So, something close to our 30 MPa concrete, that is what we are looking at, and moderate exposure, water cement ratio, etc., etc. Now, if we are adopting in Indian situation, you can take this water cement ratio permissible by Indian code only, and fineness modulus of the sand is taken as 2.40, which is required in this case, and specific gravity of fine aggregate is 2.7. Slump is same, what we are taking is 80 mm, same as before. Non-air entrained concrete we are using, because again we are only looking at the Indian scenario, and we have chosen 20 mm MSA rounded aggregate as we have done before. Right, die roded bulk density of coarse aggregate is 1600 kg per meter cube. So, this is to be measured in 3 layers. You actually measure this in 3 layers, pack them in 3 layers and in a standard manner, and measure the container volume by water displacement method, then measure the mass of the aggregate that has gone into the container. Since you know the volume and the mass, therefore, you can find out the dry roded bulk density of the coarse aggregate, which is 1600 kg per meter cube, which is, let us say as an example, is 1600 kg per meter cube. Specific gravity of the coarse aggregate is also taken as 2.7. So, first step would have been step 3, because as I said, step 3 would have been step 3 in the code, but we are considering as step 1. So, this is step 3 or step 1, actually I will say step 1. From a, for non-air entrained concrete, we have to estimate the water content, and this is the table. Now, MSA, my MSA is 20, my slump is 8 to 10 centimeter, 80 mm, therefore, my water is 200, water is 200. So, water is 200. So, this is my water content. So, water content is 200 kg per meter cube. So, that is the first step. Corresponding air content, of course, we know for 20 mm MSA. Okay, just let us see then, let us see for 25 before that. So, air content would be air content for 20 mm MSA, if you recollect, was 2%, 1% for 40 mm aggregate and 2% for this. So, this is the other information that we have obtained, and then next step is 8.3, because you see, supposing I do not have standard deviation known. So, we said average strength if not no standard deviation is known, average strength when S is known, for S unknown, for FC dash less than 34.5 greater than 20.7 is equals to FC average strength FCR dash. So, FCR dash is equals to FC plus 8.3. So, this is 25 plus 8.3 is equals to 33.3. And if I compare this cylinder strength, and if we compare with this is the cylinder strength, average cylinder strength, divided by 0.8, and I will get 4 and maybe 4.2 approximately 4 42, roughly about 42 point or 43, roughly about 43 MPa. That would be a Q strength. Now, my concrete was 31.25 some grade plus 1.65 into the standard deviation of about 4 or 5, if I take it, I think 5 by our code. So, you will have 31.25 plus, if I take 5 as a standard deviation. So, this will have another 8.25 or something. So, this will be around 39.5 or 40, let us say is close to 40. So, you see this is taking slightly higher if you look from Indian standpoint of view, it's slightly higher, this value is slightly higher, this value is slightly higher. However, step 2 is, because this is unknown, so that is why it is taking slightly higher. But if standard deviation becomes known, then this would become lower. If the standard deviation becomes known, this will become lower, because we said that it will be f c dash plus 1.34 into s. Now, s would be smaller here, let us say s is 4. So, if it is 4, then f c dash is 25 plus 1.34 into 4, and this will be equals to plus 25. So, this will be 30 plus 36, I will take it as 31, or I will take it as f c dash minus 3.5 plus 2.33 s. So, if s is 4, this value becomes 25 minus 3.5 plus 2.33 into 4, and which will give you 9.32. So, 25 plus 9.32 is minus 3.5. So, approximately it will be 31. So, this will give me 31. So, both ways I am getting actually maximum of the two, both ways I am getting actually 31. So, it will be 31 if the standard deviation is known, and if it is not known, it would have come 33.3. So, average strength would be 33.3. So, one has to decide, since we said that the standard deviation is not known. So, we will be designing for 33.3, and correspondingly I must find out. So, this is the thing, and correspondingly I must find out the water cement ratio from the table. So, from 25 it is 0.62, for 40 it is 0.43, and in between values are also given, which we have not taken, right. Now, this our value is 33.3, and corresponding to this. So, this is divided by 15. So, 0.62 minus 0.43 divided by 15 divided by 25 plus is 15. So, per MPa it would be 0.19 divided by 0.15. So, which will come out to be roughly 1.3 per MPa. So, 25 plus 33.3 or 34, let us say 34 minus, because 33.3 it was, which we will approximately 34 minus 25, which would mean that the 9 MPa, for 9 MPa water cement ratio has to be reduced into point, right. So, 0.13, this is 15. So, 15 0.013 per MPa. For 10 MPa it will be 0.13, for 9 MPa somewhat around so 0.62 minus for 9 MPa it will be 0.62 minus 0.117, and this will come out to be 3, 1, right, and 0.5. So, it will be 0.51. So, we take it as 0.51 or 0.5, we take it as 0.51 or 0.5. So, one can interpolate if it is not available, but however, actual table gives you a number of values in between. So, we assume in our case we assume a water content, let us say is 0.51. So, by use of the table, by interpolation, we can get the water cement ratio as 0.51. Now, we can find out the cement content. The water content was 200. If I take it as 0.5 approximately to ease, for ease of calculation, this will be 400 kg. I have just taken it easy, and let us say my water cement ratio specified for durability is 0.5. So, I take it as 0.400 for 400 kg, 400 kg. So, cement content is 400 kg, and I have to check whether it is more than that is required for durability, which is actually more, because for this condition we have seen IS 456-2000 gives you much lesser cement. So, 400 kg of cement with 200 kg of water is what we have got so far. The next step would be to estimation of coarse aggregate content, and this is from this particular table, and we had 20 MSA, sorry, maximum size of aggregate is 20 and fineness modulus is 240. So, therefore, 0.66 is the coarse aggregate content. So, 0.66 is the coarse aggregate content, and with this now I can find out the volume of the volume fraction. So, dry eroded 66% multiplied by, so this is the quantity of coarse aggregate that should be there. In 1 meter cube actually 600 kg of coarse aggregate goes, but the volume that would be occupied by the coarse aggregate in bulk is the 66% of the total concrete. That is what it is saying. 66% of the total concrete volume, aggregate total concrete volume will be occupied by the coarse aggregate. So, rest of the 0.44% would be occupied by, of course, the other materials, which will contain also some amount of air. So, coarse aggregate content straight away you get it, coarse aggregate contents in 1 meter cube, 66% of the meter cube is actually occupied by coarse aggregate in bulk, all right. So, in bulk, and therefore, I multiplied by bulk density, which means that there are pores inside and rest of the material will be other material. Fine aggregate content now I can determine by subtracting by the volume of coarse aggregate, cement, water, and of course, the air volume also from the total volume. So, I will total volume 1 meter cube minus actually 2% I should subtract. So, actually I should have an equation 1 minus and volume of cement also 2% air volume, air volume is 0.02. So, this has to be subtracted. Now, volume of coarse aggregate, volume of water. So, volume of coarse aggregate is given as 1056 divided by 2.7, 2700. Volume of water would be 200 divided by 1000, and volume of cement will be 400 divided by 3150. So, therefore, volume of fine aggregate you can find out, volume of fine aggregate you can find out, volume of fine aggregate you can find out, right, volume of fine aggregate you can find out, and this will come out to be this minus 0.02 also should be there because of the air content, and this will be 0.24. So, 24 is the volume. So, 0.24 multiplied by 2700 will give you the fine aggregate content. So, this is 2700 will give you fine aggregate content, and this we have found out comes out to be, this is fine aggregate, it is 2.2, this is 2.24 because 2% air content has to be subtracted. So, this value will come out to be 27 into 24 and 108. So, 64, this is how much, 27 into 24 is 648. So, I get fine aggregate content will be 648, fine aggregate content will be 648, not 700, but it will be 648 kg per meter cube. So, if I put it together, from ACI method, I will get water 200 kg, cement 400 kg, this is incorrect, this will be 648 kg per meter cube, and I will have coarse aggregate 1056 kg. So, total sum, of course, there will be some change in this, there will be less 2% because there is some amount of about 60 kg. So, this will be around 2305 kg per meter cube. So, this is how we obtain the, we can obtain the proportion through ACI method. So, if you now compare these two different methods, three different methods, step 1, I mean you can generalize, one thing you can generalize, all methods estimates water to cement ratio from strength, that we said in the first day. Water content is determined from workability, aggregate workability all from workability is determined from workability and MSA and shape of aggregate. So, W you determine from MSA, slump and shape. Water cement ratio from strength. Then cement content calculated, only next thing is to determine the coarse aggregate to fine aggregate ratio, that is determined differently by different methods. So, most of the methods determines water cement ratio from strength, water content from MSA, slump, shape of the aggregate, cement content, then you can calculate out, and coarse to fine ratio is calculated differently by different method. So, the diagram that we show in the very first class related to the general mixed design procedure, that is how it is, that is where it follows. Actually, strength is a function of water cement ratio. So, durability requirement, based on the chemical exposure, durability requirement determines the water cement ratio, and strength also governs the water cement ratio. So, whichever is lower, you choose that water cement ratio, while workability is governed by the paste content, and which also depends upon the packing characteristics of the coarse aggregate and fine aggregate system. So, it will depend upon the maximum size of aggregate, shape of the aggregate, and water content therefore is determined based on the slump, and maximum size, nominal size of aggregate, and shape of the aggregate, etc., etc. So, once these two are known, cement content is calculated, and up to this all the three methods we discussed are by and large same in some form or other. Now, once you know the water content and cement content, you can water content and water cement ratio, you can calculate out cement content. Now, three methods differ. In Indian code, you have got the proportions of fine aggregates are also specified. In the total aggregate, proportions of the fine aggregates are specified. In DOE method, proportions of total first you find out the total aggregate from wet density curves, and since you know the wet density, total aggregate content you can find out by subtracting the coarse aggregate, subtracting the cement and the water. In ACI method, then you first find out the quantity proportion of coarse aggregate in or volume proportion of coarse aggregate in the total concrete, and then multiply this by the dry eroded density, that will give you the amount of aggregate, In Indian method, you find out from the conservation of volume equation, because you know the cement content, you know the water content, proportion of fines as known to you from table, proportion of fines in the total aggregate, or proportion of coarse in the coarse aggregate in the total aggregate volume, that is known to you, and therefore, since it is known, therefore fines and coarse you can find out by setting simply two equations. So, by and large, these principles of all these methods, these two methods, three methods are same, except for the last stage of it. But in all cases, as we mentioned earlier, it is the trial mixes, it is only the first mix you can get it. The reliability of the strength water cement ratio tables as given in ACI is not reliability, their reliability in Indian scenario, they may not be applicable simply for Indian scenario, because as you recall, strength is a function of water cement ratio when all other things remain same. Now, the aggregate type, the cement properties, cement itself, they would be differing from country to country. So, this is there can be infinite possibility of strength water cement ratio relationship, because from Abram's law also we have seen there are two constants, and these two constants would actually determine the actual strength water cement ratio relationship, and this constant depends upon the aggregate type, cement type, etc., etc. So, direct use of ACI water cement ratio relationship may not be the best thing to do. The other problem, of course, associated, not problem, but the other care one must take is the ACI method actually uses cylinder strength. So, one has to be careful about using ACI method when adopting in Indian scenario. You have to take the cube strength to an equivalent cylinder strength, roughly taken as 80%. So, this is the other issue. So, keeping these 2 points together, one can actually adopt any one of this method in Indian scenario, but that gives you only the first trial. Water cement ratio is most important. Therefore, Indian code, current code of 2009 10262 definitely puts the water cement ratio should be determined from experience. It does not give you any kind of fixed guideline, which both the other methods do. So, when adopting either DOE method or ACI method, one must choose the water cement ratio, perhaps with your experience, rather than trying to choose it from table as such. But in any case, they all serve as a starting point. You have to do trial mix and find out the strength, slump, or specified properties from the mix that you have obtained, and then do the modification, and then of course, side modification towards moisture content, etc., are definitely required. Lastly, you have to actually do trial and monitor the strength also. Trial to start with, and once you have started casting, you have to monitor the strength also and modify the mix. So, mix proportion is not a static thing, it is actually a dynamic thing, and continuously it must be monitored, and the mix proportions will have to be modified. So, it is to be understood that once you have got the mix design done right in the beginning, that is not the end of it, and it cannot be used again and again without modifying and monitoring the same. So, for modifying you have to monitor. The practice of having a specified mix proportion and use it forever is not correct. So, one has to monitor it and modify it continuously. Anyway, so with this note of summarizing these three methods, we would like to conclude our discussion that we have seen that these are the 4 proportions we have already seen, and we can summarize that today we have discussed ACI method, earlier we have discussed DOE and Indian method, and we have also discussed somewhat about the comparison of these 3 methods and where how can you adopt them in Indian scenario. I think with this we will conclude. Thank you very much.